We're given this differential equation and told that the question concerns its solutions. We're going to be using the fact that if y and its derivatives satisfy this equation, then y is a solution to the equation. It then says, for each value of k, let yk of x be the solution of star, which is the given differential equation, that satisfies yk of 1 is equal to 1. So we might have some solution y that satisfies equation star, but when we plug in x equals 1 into the expression for y, we get a value of 2, say. And that would mean that the solution we have is not the particular solution yk that we're concerned with here. Also note that if some solution satisfies equation star, then it does so for all values of x. We wouldn't at any point need to plug x equals 1 into equation star, as that wouldn't tell us anything. Next it says, you may assume that there is only one such solution for each value of k. What that means is, suppose we have some solution y that satisfies equation star, and has a value of 1 when x is equal to 1. Then we can conclude that that solution is the unique solution yk that we're concerned with here. Note that there's a unique solution for each value of k, corresponding to the k terms in the differential equation. Now, part 1 says, write down the differential equation satisfied by y1 and verify that y1 of x is equal to x. So by the definition of yk, we need to set k equal to 1 in equation star, and then verify that y equals x satisfies equation star. If it does, then we just need to check that when we plug in x equals 1, we get a value of 1. And if we do, then we can conclude by the uniqueness of the solutions that the solution is, in fact, the particular solution y1. Note that for the whole of this question, y is always a function of x, so rather than writing y of x explicitly, I just write y and any subscripts. The first line here just says that k being equal to 1 implies that the differential equation star now looks like that. Now notice that the second line says that y rather than y1 is equal to x. The idea here is, rather than assuming that y1 is equal to x, just to let x be some general solution y for the time being, and then show that that solution has all the properties of y1. The third line shows that when we plug y equals x into equation star, we get 1 minus x squared plus x squared on the left hand side, which is equal to 1, and that's what we have on the right hand side. So y equals x satisfies the equation star. Not only that, but when we plug x equals 1 in, we get a value of 1. Now the question tells us that if some solution satisfies star with k equal to 1, and it has a value of 1 for x equal to 1, then that solution must be y1. So we can conclude that y1 is equal to x. Now part 2 is very similar to part 1, only with a slightly more complicated expression for y. And when that happens in a step question, it's usually to give some opportunity to become familiar with a new definition in preparation for using it in a more challenging way. So the best approach is not just to focus on getting the right answer, but to really pay attention to how the answer comes about. The working here is analogous to the previous case. The first line is just setting k equal to 2 in the expression star. The second line is taking the derivative of the new expression for y. And the third line is plugging y and its derivative into the equation star and showing that the equation is satisfied. Again, verifying the initial condition, showing that the solution y passes through the point with coordinates 1, 1. The conclusion is that the solution y must be the unique solution y2. The important point to take into the end of this question is that here, for instance, we have y2. Now, we know something about y2. We know that it satisfies the differential equation star when k is equal to 2. So if, for instance, we wanted to express y2 in terms of its first derivative, we could do so by rearranging equation star. So for part 3, we're given this expression for z in terms of yn, and we're told to show that it satisfies an equation. So taking the derivative of z and plugging it into the left-hand side of the equation, if we can then show that that is equal to 4n squared, which is on the right-hand side of the equation, then we can conclude that z satisfies the equation. However, we have this complicated expression that looks unlikely to be equal to 4n squared, so we're going to need to make a substitution. The thing to notice here is that we have terms in yn and its derivative. So if we set k equal to n in equation star, then we can express either yn in terms of its derivative or the other way around, whichever would be most convenient. So considering equation star then, we have this 1 minus x squared term multiplied by the square of the derivative. And notice that, comparing that to the first term here, if we take out a factor of 4yn all squared, then we can express the rest of the term as n squared minus n squared y squared. And now the expression can be shown to multiply out to 4n squared. So z satisfies equation star with k equal to 2n. And what does that mean about z? Well, going back to the definition, any solution that satisfies equation star when k is equal to 2n must be y2n if it satisfies the initial condition of being equal to 1 when x is equal to 1. So checking that then, we find that when x is equal to 1, yn is equal to 1 by definition. And the expression for z is 2yn squared minus 1, so when we plug a value of 1 into that for yn, we find that z is equal to 1 also. And therefore we can conclude that z is equal to y2n. Part 4 says, let v of x be equal to yn of ym of x. And we're told to show that v of x is equal to ymn of x. For this part we're going to need the chain rule. If we have some composite function f of g of x, then when differentiating with respect to x, we must multiply by the derivative of g of x. So we're told to show that v of x is equal to ymn of x. Now what do we know about ymn of x? Well, from the definition of yk, we know that if we set k equal to mn in equation star, then ymn satisfies equation star, and it has a value of 1 when x is equal to 1. So if we can show that v of x has those properties, then we can conclude that v of x is equal to ymn of x. The first line here is just differentiating v using the chain rule for composite functions. So this time, rather than doing the algebra followed by the conclusion, the strategy is to explain the argument and then do the algebra, so that if the algebra goes wrong, marks will still be given for describing the method. And this is generally a good approach in STEP when the algebra gets difficult. The first line of the note just deals with the fact that if v is one of the particular solutions yk for some k, which in this case will be mn, then it must have a value of 1 when x is equal to 1. And the argument here uses the fact that we're told that yk of 1 is equal to 1 for all k, including m and n. Now, since v satisfies this condition, if it can be shown that v in its given form also satisfies equation star with k equal to mn, then we can conclude that v is the particular solution ymn. So substituting v and its first derivative into the left-hand side of equation star gives this. And if it can be shown that this is equal to mn all squared, which is the right-hand side of equation star, then we can conclude that v satisfies equation star. Again, we're going to have to make at least one substitution. Now notice that in both terms we have these composite functions, and for those, the version of equation star that we need to consider is the one that we get by setting k equal to n. Now, just as an aside, I'd like to demonstrate one mistake that it can be tempting to make here. In the first line is equation star with k equal to n. We're going to be plodding along and substituting y and its first derivative into equation star, as we have done in the previous parts of the question. But why would that be invalid? Consider again the definition of yk of x. Remember that in the solution being presented here, a notational choice has been made to omit the explicit dependence of the functions yk on x, so for instance writing yk instead of yk of x. Notice that yk of x is defined in relation to equation star, and that the input x corresponds to each instance of x in the differential equation, including the differential term. X here is just a dummy variable, or a placeholder. We could decide that we want to change the input variable to t, or u, or anything at all. But if we did, we'd have to make the corresponding changes in equation star. It might seem strange that we have ym presumably being a dependent variable one minute and then an independent variable the next. We can think of equation star as operating on different levels. On one level it takes x as an input and gives a value for ym. It then takes the value for ym as an input in some other version of equation star and gives a higher level output. So that output is going to depend on the original input. Now the idea behind this final part of the question is that we can take this two-stage process of getting an output, putting it back in and getting a final output, and replace it with a single operation by choosing the value of k appropriately. So we need to decide on a substitution here. You might be relieved to hear that step algebra doesn't get much more difficult than this. Consider the first term in square brackets, and note that it was derived using the chain rule. That's to say, by differentiation with respect to x, rather than with respect to the input variable, which is ym. However, in equation star, we have a derivative with respect to the input variable. So this would be a useful form of equation star then, with ym as the input variable. And notice that differentiation here doesn't require use of the chain rule. And that's because it's effectively as though we don't have a composite function. Ym is being treated as an input variable, rather than as a function in its own right. So the first term in square brackets then does not appear in its entirety in any version of equation star, so that leaves us to decide on the best way to separate it out. Notice that the square of the derivative of ym can be paired up with the 1 minus x squared term to give a product which does appear in some version of equation star. Also, the second term in square brackets and the n squared term alongside it appear together in the version of equation star that we just considered. Now, if this all seems overwhelming, try to appreciate that these two substitutions are just about the only two sensible possibilities. Consider the first part of the first term in square brackets, the derivative of yn evaluated at ym. Suppose we were to substitute for that, then we'd get a hefty expression with a denominator. And so really, the only question is, do we need to make one or both of the sensible substitutions? Well, after making one of them, it becomes clear that the other one is also necessary. The second line now multiplies out to m squared, n squared, and so the conclusion follows.